the final efficiency. So the opponents already challenged the reporter for the question challenging 40, right? And next they accept that we are moved on the next stage. The reporter has to prepare the talk for 5 minutes. Come on. Okay, thank you. Sorry, the leaders have to sign the next form.
I'm from Team Excelsior. Today what I'm going to report is problem number 14, ball on membrane. This is the problem statement. When dropping a metal ball on a rubber membrane stretched over a plastic cup, a sound can occur. Explain the origin of this sound and explore how the characteristics of the sound depends on the relevant parameters. And my main focus is investigate of the origin of the sound and how characteristic of the sound is set by the relevant parameters. Here's my reporter's outline. First, I'll show the preliminary experiment, including the observation and qualitative explanation. And for the theory, we consist the wave equation and the boundary condition about the vessel function. And the experiments, the parameters like bounce radius and delegation and shape of the membrane. And finally, conclusion. Here's a preliminary experiment. Here's the observation. You can see when we record the sound and we, by analyzing it in this spectrum, we can see there are some obvious peaks right here. Here's a qualitative explanation. When the metal ball collides with the membrane, it causes the membrane to vibrate and also causes the air particle to vibrate. And instead, the collision of the metal ball causes the membrane to have standing wave, which causes the sound to be resonance. And here's the theory. When we consider the x and y coordinates into the polar coordinates, we can transfer our notation in this to this. And the wave equation, we can describe the u of three terms, which depends on the r and the theta and the t. And by substituting the u into the wave equation, we can get this equation. And for the h terms, we will let it equals to negative m squared. And the solution of the h is cosine of theta. And we will let the v terms equals to minus omega squared over e squared. And we can know that the t will equals to sine omega t. And we will substitute the h and the t into the previous equation. And we will let the rho equals to kr, and we will get this equation will equals to 0. Then by calculating, we can know that the Jm of rho will equals to this equation. Hence, the u can be described as the amplitude, a Jm, and cosine sine function. Then we substitute the u back to the wave equation, and we will let rho equals to kr, and lead us to this. We can know this equation, and we find that this equation is the Bessel equation. So we can know that the Jm is Bessel function, and this is the graph of Bessel function. When the membrane stretches over a cup, it will have boundary condition, which is when at the edge of the cup, the amplitude will be 0. And the other boundary condition is the solution of Bessel function will equals to 0. And we define the rho mn equals to the solution of the Bessel function. And knowing that the u equals to this, so the k, which is the wave number, will depend on the rho mn, which is the solution of the Bessel function. And by that, we can know the frequency will look like this. And we can also calculate the wave speed by using this equation. Here's a simulation of the Bessel function. You can see that this is J02 and this is J11. For one situation is when the ball collides the membrane in the center of it, it causes a deformation and looks like this. The cross-section of it looks like this, and it fits the Bessel function J02 function. Another situation when the ball collides with the membrane, it causes a deformation and looks like this. The cross-section of this membrane looks like this, so we can know that this fits the J11 function. This is a very verification. You can see when giving it a certain frequency, it causes the membrane to vibrate like this. So we can know that it shakes in the two parts of the membrane, so this fits the J11 function. And the other one, it will shake in the four parts. The resonance of the membrane is like this, which is the J21 function. And here's my experiment about the setup and bounce radius, elongation, and shape of the membrane. And first, I will measure the tension of the membrane by using this way. We will, because measuring the tension of the membrane can calculate the wave speed to do our experiment. First, we will control three sides of the membrane to be the same, and we will pull here by the tension meter. And when the elongation of each part of the membrane is same, the tension of each are the same. So by our experiment, we can know our elastic constant equal to 871 Newton per each centimeter. And another experiment about the aerial density, because of the radius of the curve is the same, so the tension of it might change the aerial density of the membrane. So by doing our experiment, we can know our function, like the aerial density between the elongation looks like this. And here's our equivalent. This is our experiment setup. First, we'll connect the metal ball with an electromagnet, and then we'll drop the metal ball by electromagnet and let it collide with the membrane and capture the sound by the microphone. Here's our first experiment about the bending position, circular one. This is a spectral graph of the sound generated. You can see that some obvious peak of these, and these fits the equation here, where the rho element is the solution of Bessel function, like this. And because compared to our experiment, the R is where the landing position to the center of the membrane, and the unit is centimeter. You can see that they will almost have the same peak because the frequency won't be affected by where you collide with the ball, collide with the membrane. But when you see at this peak, the sound intensity, when the R increase, the sound intensity decrease. That's because this is the J01 function. And when the ball collide with the membrane in the center of it, it causes big vibration. But when the ball collides nearly in the edge, it causes less vibration of it. So we can see by this graph. And another experiment about the elongation of circular membrane. We change the elongation of the membrane, and we are going to measure the frequency. And here you can see an obvious peak right here when the elongation is 0.1 centimeters. And by increasing the elongation, the peak starts to shift rightward, and it will look like this. And for the experiment compared to a theory, we can know by this equation, knowing that the speed, which is the wave speed of the membrane, will be proportional to the frequency. So this is our experiment to compare with it. And next experiment is about the radius of the cup, the circular cup. And the parameters are the radius of the cup, which is 3.5 and 3.9, 4.9, and 5.6 centimeters. And what you are going to measure is the frequency. And this is our control variable. This is a graph of it. You can see when the radius of the membrane is small, when increasing the radius of the membrane, the frequency will shift leftward like this. And by knowing this equation, the radius of the cup will be inverse proportional to the frequency. So this is our straight line compared to the experiment. And the possible error is we measured our elongation by hand, so it might cause the elongation to be different, which may affect the wave speed. And here's another experiment about sound interval. You can see when the ball collides with the membrane, it generates sound. But each sound, the sound interval is not the same. And so for the explanation of it is when the elongation is small, it causes small tension of it. So the y component, which is the vertical component, will be small. And when the elongation is big, the tension of the membrane is also big. So the vertical component, which drives the ball to rebound, is bigger, like this. And here's the experiment with it. The delta x is the elongation, and the delta t is the sound interval. You can see at this graph, when increasing the elongation, it decreases the sound interval too. And we can calculate our coefficient of restitution by using this equation. And this is our experiment compared to it. You can see when the elongation increases, the coefficient of restitution also increases too. So by using this equation. And discussion about the air resonance. You can see that there are one peak or more. There are some peaks that our non-Bessel function has predicted. because we use our microphone to capture the sound, which has the air resonance by using this equation. And the other discussion about the deformation of a colliding ball. You can see that the ball collides the membrane, it causes deformation. But when the ball leaves the membrane, the deformation is small. So we only capture the sound only when the ball leaves the membrane. And finally, my conclusion. Conclusion about this is the first peak of the vessel function J01 function. You can see that the J01 function looks like this. So when you collide your ball in the center of the membrane, it causes big vibration. So it means that the ball collision is more similar to the J01 function. But when the ball collides near the edge of the membrane, it doesn't look so similar to the J01 function. So the sound will decrease. And here's the conclusion about the elongation. By using this equation, we can know that the wave speed, which will be influenced by the delta x, which is the elongation, will be proportional to the frequency of it. And this is our experimental proof. And for the experiment about the radius of the circular plane, the frequency will be inverse proportional to the radius of the curve, and where the rho 1 will equal to this. And the possible error is caused by when we stretch our membrane, sometimes it's hard to measure all the points of the elongation is the same. So the experiment error is caused by this reason. And thanks for listening.
Thanks for the report. The first question I want to ask is that you use Fourier analysis, right?
Yes, right.
Okay. So, what's the beginning of the time of your report? When the first drop or
41. Yes, the first drop when the ball leaves the membrane.
Okay. So you record the sound from the first drop to the last drop, or
No,
just
we
the
only
first?
the first drop.
Okay. So then, when do you end your report?
And the record when the sound totally can be recorded. Because when the sound is very small, when you do FFT, it will consist of other sound from the root part sound.
Okay. So I think in your report you said that the phase diameter will only influence the frequency, not the amplitude, right?
Yes, because our vessel function in our theory can only explain the frequency of it, and which the frequency looks like this equation.
So will the size or mass of the ball affect the amplitude or frequency?
The size will affect the frequency of it, and the amplitude we cannot know by our theory. But by FT, we can know that when the frequency increase, the sound intensity will decrease. Because of when the ball collides with the membrane, the energy given by the ball to the membrane is the constant. So when the membrane vibrates faster, it needs to have less sound intensity.
Okay. For example, the first drop and the second drop, do you compare the average drop of the line?
Time is up. So you have 3 minutes to prepare.
my position from the rotating ball membrane. Okay, I'll repeat this again. When dropping a metal ball on the rubber membrane stretched over a plastic cup, the sound can be heard. Explain the origin of this sound and explore how its characteristics depend on relevant terrain. Okay, these are some pros and cons of the report. They use theoretical model and simple understandable qualitative explanation of methods and phenomena. Appropriate use of media and graphs, including lots of philosophers and great understanding of complicated functions. But however, they lack explanation of exact parameters in theory and accurate predictions of experiments and investigation on graphic details. Here are some pros and cons about experiment essay. They have a reproducible setup made trials and took advantage of graphs for clear statements. Accurate experimental setup in degrees for almost external forces that affect. So I think they did not do the measurement of even distribution and the functions are not experimentally verified and some details are accurately constructed. These are 3 points I want to discuss in 10 minutes. What's the beginning point of the Fourier transform? And how to predict this phenomenon? And the third one is how can you do an experiment besides of tensory? And that's the end of my position. Okay, I want to start the discussion. My first question is that if you record the sound from each drop, yes.
In our experiment, we only capture 1 drop of the ball because when colliding, the colliding time won't affect the frequency as our experiment shows.
Then will it influence the amplitude?
When releasing height is higher, the ball will give energy to the membrane. When the middle ball collides with the membrane, it causes the energy transform and causes the membrane to vibrate. So when the middle ball given by the membrane gives to the membrane more energy, it causes higher amplitude.
So do you compare the first drop or the second drop, like the amplitude from each drop?
Again. You can see in this graph, when this is the times, the colliding times, each times. The delta t, which is caused by the height of the ball decrease. So when you release the ball here, it will start to rebound, and the rebound time will decrease like this.
Can you go to slide page 41? Okay. So for this part, can you show the video again? Okay.
Like this.
Yes. So I think you investigate the height of the membrane of each drop. Do you think
this video didn't consist the height of the dropping the ball.
all right. So do you think that the ball, if you drop it in the middle, will it the next drop is dropping outside the middle?
Oh, it may cause by when you collide the ball in the different parts. This part of tension could be not be the same when the vertical axis is not the same. It may bounce into the other directions.
Can you explain where does the sound come from in a simple sentence?
Membrane.
Come from the membrane. From like the inside or of the cup or the outside or just the membrane itself?
Like this qualitative explanation shows the metal ball causes the membrane to vibrate and also causes the air particle to vibrate, and then you can hear the sound.
Okay. Can you go to page slide 22? Okay. So here, you investigate the landing position, right?
Yes.
Okay. So how will there be a connection between the landing position and the frequency? Like
the frequency as this spectrum shows, because our formula doesn't consist of any position of it, so it will only affect by the rho element, which is the solution of the vessel function, and the wave speed and the radius of the So we can know as this graph shows the lower limit, which is the solution of vessel function, will increase. So by prediction, we can know this peak is F01, and this peak is F01, and this is F21, and so on.
Okay. So I think in your experimental setup, you put the microphone on the top. Yes. Yes. Okay. So do you think if I put the microphone beside the membrane, the sound will be the same?
The sound generated by the membrane will be the same, but as you capture and to analyze it, the decibel will not be same. Because when the air vibrates, it will vibrate. When the distance increase, the volume will decrease. So when the microphone is larger distance between the membrane, the sound intensity will decrease. The recording sound intensity will decrease.
Okay. So as you said, you investigate the Fourier transform of each drop graph. Okay. And this is okay. As you mentioned, that you record it just one drop. So
yes. Because every you can.
Okay. So I mean, do you think that for a specific time you can investigate the frequency? Yes, this is for a period.
This is for a period of vibration.
Yeah.
So what you are asking is, will the sound be not same when the dropping time?
No, I'm asking like if you drop it and for instance we call that time is 0. Okay. So can you investigate the like for instance if the time is 0.1, then what specific frequency or decibel is created?
Because when the ball giving the energy to the membrane will have standing wave, which will cause air resonance. So when the ball collides with the membrane, the period of time or the instant of time, all of the frequency will be generated. Because the ball cause the membrane vibrate, the membrane will have standing wave.
Yes.
The standing wave will cause air resonance, and the air resonance will generate these peak. So no matter when you collide with the ball or a period, it will generate same peak.
So do you mean like if you record it for example 1 second, then the graph will be the same as you record it for like
Yes.
0.5 seconds?
Yes.
Oh.
We can describe it in our theory. Please turn to page 14. Our theory only describes that the frequency will be influenced by this. So it doesn't include the time. It doesn't include the time frames. So the frequency won't be affected by the recording period of the experiment.
May I go to the like sure. For sound, I mean, this is the drop. The time is 0, and you record it to like, for example, from time to 1, and I think the amplitude will decrease as time goes.
You think like this?
The amplitude, yes, like this. So do you mean if I record it from here to, for example?
Each part of and when you see closer, the vibration will make it look like this. The sound intensity increase, that is because the air friction. The air friction causes the membrane to vibrate smaller.
Okay.
But the frequency will also be the same because it is a standing wave. So no matter what the time or where you record it is, the frequency will always look like this. But the intensity will not be the same.
Okay. So I will want to ask you for not the first drop, but if you drop the ball on the membrane and drop for sometimes, and you it's the last few drops, for example, the initial height and for example like this, and as
You mean the releasing height of the ball is not the same?
yes. No. It's the same drop, but not the same.
Same releasing height. The reporter thinks that it is another way to describe the releasing height that causes the sound intensity. So when you rebound here and rebound again, the frequency will be the same, but the sound intensity won't be the same because the energy giving the membrane is not the same.
So do you mean that for each drop the frequency will be the same even if it's just bouncing? Not bouncing, it's like floating.
When floating on the membrane, this is not the membrane vibration. Because
then what causes the sound here?
when here there will be no sound. So our experiment only capture our experiment only capture one collision of the membrane, and when the ball will rebound out, and so we can capture the sound.
So basically, your experiment, you don't investigate the last few sounds. You mean the last few drops will not directly floating on the membrane, and there will be no sound.
Yes, we did not discuss about it because please do very important. When the ball is on the membrane like this, it's really on the membrane, not the property. When the ball is on the membrane, it causes the mass of the membrane to some kind of increase the mass of the membrane. So it could not vibrate that much.
Okay. Yeah. But in my view, do you agree that if there is a sound, then what's the time that or what's the height that it will become no sound? Because when it's floating there will be a gap between.
Everything will have sound, even for this ground chord, but it is just hard. It is hard to measure.
Okay, so you can measure this sound.
Yes, and I want to answer my question again. When the ball is right here, it causes a boundary condition to result in different. So when the ball is on the middle or center of the membrane, it will not fit the boundary condition of it. The boundary condition will not be same. So the vibration of the membrane maybe this time is not the best solution. It may result in
Okay. So I want to go to some experimental details. How do you make sure the membrane is steady?
what do you define as steady?
Steady, like you won't. I think in your experiment setup as a picture, I saw a thing that holds the membrane.
Oh, you mean the tension measuring?
Yes.
The tension measuring, we make sure that each point of elongation is the same. So, when the elongation of each membrane is the same, the tension of it will be the same.
Okay. Now let's see. So I want to summarize this discussion. I asked the reporter about how will the difference between the recording length of time, and the reporter said that the frequency will not change even if I record it for different time length. But however, I think that it will cause it to be different. The second thing is that I asked that the sound of the last few floats or last few drops, and the reporter replied that it's not easy for us to investigate or hear the sound. But however, I think that that sound could be different from the first few drops because it's floating, not just dropping on it, and its frequency. Also, the amplitude will be different. And that's the end of my summary.
That's all. So the viewer, you have 3 minutes.
Alright, we'll do this away the opponents. Here I have some questions for both. So first, please turn your page 36. So in your experiment, the ball holds up to the center or the side.
This is just a demonstration of the ball colliding with the membrane.
So if a different location will cause different vibration. Well, for example, 0, 1 or 1, 1.
The 0, 1 and 1 is caused by the vessel function solution and result in different. So it only causes a resonance of the membrane to result in different.
So will it influence the frequencies with the locations different?
it only affects the frequency when you only make sure the membrane, the deformation of membrane only fits some weight features, right?
Okay, thank you.
Yeah.
And how about opponents? Do you agree with the reporter?
You mean with the different phases of the drop, it will influence the frequency?
Yeah.
Yes, I do think it will influence it.
Do you think it will influence?
Yes.
Okay, so the second question, please turn to page 27. So, 27, please. So, the 01 is the fundamental frequency, right?
Do you mean at 01?
Yeah.
Yes.
So, what is the sound that you detected before the fundamental frequency?
Because the lower end, the lowest, the minimum lower end is that costs the F01. So there will be no lower frequency of it.
I'm talking about these.
These frequencies, this frequency is caused by when we record the membrane sounds, and also records the sound from each.
So how do you deal with the surrounding noise in your experiment?
Because we can know that there are an obvious peak, and the sound intensity is enormous difference.
I see. And how about this peak here?
This peak air resonance. Please turn to page 40. This is caused by the air resonance, which the frequency of this might be multiplied, and it will equal to this.
Okay, I see. So here's a question for both of you. So you're talking about the membrane most, and how about the cup? What is the function of the cup?
The function of cup, 14. The function of the cup will affect the boundary condition of it.
I see. And how about the opponent's idea?
I think the diameter will only influence the frequency.
I see. So, and the next question is, do you consider the vibration of the cup?
We did not consider about it.
And how about opponents? Do you think that is, if it's necessary?
It's necessary, but we can go
Hands up.
Thank you.
手也是后面也是可以配。Okay, the reviewer, should we take the floor?
Our proposition for the opponents, I'm going to review for the problem of the wall of the membrane. So here's the problem statement, and I believe the focus of the problem is the following. The first one is the investigation of the origin of the sound, and second is how characteristics of the sound affected the relevant parameters. Next. So here is the summary of the reporter's presentation. So for the phenomenon, when the ball falls onto the membrane, the sound can be heard. And for the theory, they talk about the wave equation, the boundary condition, and basic function. And for the experiment, it is including elongation, which is the circular elongation, and area density, and landing position. Additionally, radius of the cup and collision intervals. Now I'll elaborate on some of the pros and cons for the report. So start with the pros. They have good observation video for the phenomenon and a clear illustration for the modeling. Also, they have employed Basel function to support this theory. Also, well-considered experiment setup and clear graph for the analysis of the results. However, for the cons, they lack of parameters like different material of membrane, and they do not have enough explanation for the outside factors, for example, the background noise. And they fail to compare theoretical assumptions to the experimental result. And here's the remarks for the opponents. So they're talking about what the report said, their pros and cons, and further discussions. And the pros, they summarize the report's presentation concisely. Additionally, they help clarify some missing points in the report's presentation, and for the reports to improve, including bringing out several irrelevant questions for the report during the discussion. Additionally, they delve into the deeper and further discussion. Here's the discussion. So first, the opponent asks when to start and stop the report of their experiment. So the report answer start at the moment of the first ball and stop when the sound can no longer be recorded. And the second one is the opponent asks, can you investigate the frequency of a certain time? The report said no matter when you investigate, the peak is always the same. For this question, we agree with the report. And here's the third discussion. The opponent asks, how will the response of the ball affect the results? The reporter answered, when the ball rebounds, the sound frequency will be the same. And for the problem, our view is agreeing with the report. Here's another discussion. The opponent asks, the connection between the location and the frequency. The report said it will only be influenced by factors such as wavelength and so on. But we believe there are more factors to discuss, for example, the difference of tension. And here's another discussion. The reviewer me asked the landing location of the ball and the relationship to the fundamental frequency. The reporter said no, and the opponent said yes. For the reviewer, we believe the landing location of the ball will not influence frequency. And the discussion, I asked how to reduce the sound noise, and the reporter answered only observe the peak of the sound. And I suggest that they can do more on their experiments, like they can record the noise of the sound and take it out of their analysis. And this discussion, the function of the plastic cup, the report said the cup will influence the boundary condition, and the report said that he agrees with the reporter. And here's the missing points. The first one, they lack different heights and tension in their analyses. The second, the error bars on the graph, for example, page 23 and 32 is not included, and the reduction of background noise is not included, and the explanation for the cup is not really concise. And the different shape of the membrane is not included. Thank you.
Here's my concluding. The ball is a membrane which causes it to vibrate, and we measure about the tension level, about the membrane and the parameters, and we measure the sound when the ball leaves the membrane, and analysis the frequency and intensity of the sound. A possible error may caused by the measure of the negation, and the discussion about the errorsness. Here's my remark. Our theory can predict the frequency, which the Basel function here is the rho the solution of it will equal to this. And we can predict the frequency by this one. And the size of the ball will not affect the frequency, and the releasing height will affect the energy given to the membrane wood, which affects the amplitude. The membrane vibrate also let the air to vibrate, so the sound can be heard. Our theory mentioned that the frequency will not affect by the time pass, and the position of the microphone will only affect the dB, which is the relative intensity, sound intensity. And our main focus is the origin of the sound, which is caused by the membrane. And there's no need to consider the resonance of the cup. Thank you.
Okay, so the final one, any question or comment from the viewer?
So I have a question for all the team. So obviously that there are many parameters to investigate this process. So I just raise one question. So suppose you have boundary condition that is flexible. So it's in between fixed boundary condition and free boundary condition when you study in the way. So suppose the cup is a plastic material. So that is not really it's in between fixed boundary condition and free boundary condition. So if you comment that for this boundary condition, how we would change the frequency of the sound. Okay, let's start with the review.
Can I make sure the question is about the material of
the cup, so that is I mean if you use the solid cup, then it would be something like a fixed boundary condition, right? And in this case, because you need the tension, so you cannot create the free boundary condition. So suppose that I'm using the flexible plastic cup, so the vibration can, so the vibration of the membrane propagate to the boundary. So it would also vibrate with the membrane. And so that boundary would be in between fixed boundary condition and free boundary condition. So in this case, how this boundary condition will change the frequency.
First, I want to talk about how different materials of the cup will influence the result. If it's flexible, how will the result be? So, because we may have to consider the natural frequency of the sound, which may cause certain frequency of the spectrum, the amplitude to become louder. So it may cause the difference in the graph of the sound level.
That's it. And how about the opponent?
I just want to clarify the problem again. That the vibration of the cup with the membrane affects.
Right. So right now I don't have the boundary of the membrane is not fixed in the space. It's not totally free, but it's flexible, so it can vibrate. So in this case, that you have a boundary in between free boundary condition and fixed boundary condition, and how would that boundary condition change your frequency of the sound?
I think that the frequency of the sound will change because it vibrates because it's a vibrate. All the cup, both the cup and membrane is vibrating. So I think it does affect the frequency, but of the amplitude I didn't understand.
Is your question, well, when changing the boundary condition, what will affect the frequency?
Yeah. I mean,
We have done so many experiments, so we can only put the other sides of membrane to the back of page. The boundary condition of a square membrane looks like
I
this.
think that the still using the circular boundary condition, but the boundary condition can change the size.
Change the size.
The softer plastic one, right? And which the metal part, for example, like that. So that's this kind of circular boundary condition.
This
Yeah.
we change the radius of the curve.
Kind of the boundary condition is softer or not.
The current boundary condition is the same. It's when the r, which is the distance between the middle, equals to the capital R, which is the radius of the curve.
No, just give the answer, short answer. Do you expect to see a frequency change of something?
Yes.
Any comments? You okay? Sure. Okay, yeah,
just
sure.
a comment, but not related to this question. Because in the morning section that I heard a talk on this problem, I am sure that it's not your team, but they are using very similar transparencies for the communications. So usually, sometimes that one school can have two teams, and sometimes they will correctly use each other. But including data, you take your own data and you do your own analysis. You don't share the usual PowerPoint. So all the figures, all the data, analysis, and theory, you have to do with yours by yourself. Not just have. I don't know who coming. Who I don't have to say. But I'm just saying that I mean this is because this fight that before we didn't make very clear that this is not we do not encourage that to share the PowerPoint. Well, you see that would not be fair. If you have two teams, you have 10 people working on the same PowerPoint, but the other school may have just one team. And so I'm just this is not clear enough before. I think that so there will be no we don't do any decision on this. But in the future, that will make it clear that we do not encourage this kind of collaboration. The collaboration you can work together, that is fine. But you take your own data, you do your own analysis, you prepare your own PowerPoint. Okay.
Okay. So after that, we have to write a score. So when you're ready, Okay, so we will give a score to the report. 7, 8, 6, 9, and 7. Okay, we will give a score to opponent. 7, 6, 7, 8, 6. And the final one is give a score to reviewer. 8, 7, 8, 9, 6. Thank you. So we close our session. Thank you for your participation.